Section 9.2 Part 5 Confidence Intervals for a Population Mean. Lesson Objectives: Interpret a confidence interval for a population mean. Understand the role of margin of error in constructing the confidence interval. Lesson Objective: This is our interpretation template, so when we estimate the population mean using a confidence interval, this is the template that we want to use. We start by saying we state the level of confidence. It's either going to be a 90, 95, or 99. That will be given in the problem. Then we say confident that the true population mean, and then we put that in terms of the problem, is between, we state the lower limit, then we say and, then we state the upper limit, and we include the units. Let's look at a visual. The horizontal segments represent 90% confidence intervals for different samples of the same size. In the long run, 9 of every 10 such intervals will contain mu. So here's some things to keep in mind when we are interpreting the results of a confidence interval. The value of mu is a fixed number. It is either in the confidence interval or it's not. It is incorrect to say there is a 90% probability that an actual mean is in the interval between 22.3 and 23.5. So what is correct? If a large number of samples is collected and the confidence interval is created for each sample, approximately 90% of those intervals will contain mu. The only problem is we don't know when we do a confidence interval if it really contains the population mean or not. That's why we have to talk about in terms of probability. Let's do an example. If you recall, this is the text messages example. We want to construct a 90% confidence interval for the population mean number of texts per month for a typical college student aged 18 to 24. Now, if you recall, we computed the confidence interval in a previous video. So now we're going to interpret this confidence interval. We would say we are 90% confident that the true population mean number of texts per month for a typical college student 18 to 24 years old is between 717.95 and 740.05 texts. Let's do another example, the Facebook example. We want to interpret the 95% confidence interval for the mean number of friends for all users of Facebook. So if you recall, our confidence interval is here. So if we interpret this confidence interval, we would say we are 95% confident the true population mean number of friends on Facebook is between 114.4 and 147.2 friends. If you recall the commute time, how far one way does the average community college student commute to the college each day for this certain college? From the sample of 300, X bar was 15.22 and S was 5.95. We want to interpret this interval with a confidence level of 95%. So if you recall, this was the confidence interval. To interpret this, we would say we are 95% confident that the true population mean one-way distance to college commuted by a community college student each day is between 14.54 and 15.9 miles. If you recall the example weights of pennies, we had a sample of 17 pennies minute after 1982. They were weighed and measured in grams. If you recall, this was the 99% confidence interval. So to interpret this confidence interval, we would say we are 99% confident that the true population mean weight of pennies minute after 1982 is between 2.452 and 2.477 grams. Now this is a new example. Suppose that a highway safety researcher is conducting the design of a highway sign and is interested in the mean maximum distance at which drivers are able to read the sign. The maximum distances measured in feet in which n equals 16 drivers can read the signs are as follow. We have the raw data, 16 values. We want to construct and interpret the 99% confidence interval for the mean maximum distance a driver can read a sign. Because our sample size is less than 30, we have to check the assumption that the original population needs to be normal. We do that by the probability plot or QQ plot. This is the probability plot in Minitab. We see all the data points are within our bands, so this gives evidence that the original population is normal. Then I computed the one sample t using a 99% confidence level, and here's our confidence interval. So to interpret this, we would say we are 99% confident that the true population mean maximum distance at which drivers are able to read the sign is between 417.9 and 549.6 feet. Lesson objective. The margin of error, denoted capital E, or sometimes MOE, in a 1 minus alpha times 100% confidence interval is given by this formula. This is our critical t-value that comes from table 6, and this is our standard error, where S is the sample standard deviation, N is the sample size. And again, we are requiring that the population which the sample was drawn to be normally distributed if the sample size is less than 30. Sample size is larger than 30, then the central limit theorem says that the distribution of x bar will be normal. So here's a visual. Whenever we have a confidence interval for the population mean, x bar is always exactly in the middle, and we subtract the margin of error, we get our lower limit. If we add the margin of error, we get our upper limit. So the margin of error depends upon three factors. The level of confidence. As the level of confidence increases, margin of error also increases. Number 2, the sample size. As the size of a random sample increases, the margin of error decreases. Number 3, the more spread there is in a population, the wider our confidence interval will be for a given level of confidence. So the more spread is in a population, when we take a sample from that population, it's going to have more spread. Let's look at a visual. Here is a 90% confidence interval for a population mean mu, and if we go to a 95, we see that our margin of error increases. We are more likely to catch the true mean, but the confidence interval is wider. Let's do an example. Construct a 90% confidence interval for the mean weight of pennies minute after 1982. Comment on the effect that decreasing the level of confidence has on the margin of error. So this is our same example that we did in previous videos. First thing we need to do is calculate critical t-value. So our degrees of freedom are 16, and our alpha divided by 2 is 5%. That gives us critical t-value of 1.746 using table 6. Thus the lower bound will be our point estimate minus the margin of error. So here's our critical t-value. This is S, and then we have our square root of our sample size. Rounded to 3 decimal places, this gives 2.457. When we do the upper limit, we get 2.472. To interpret this confidence interval, we are 90% confident that the true population mean weight of pennies minute after 1982 is between 2.456 and 2.472 grams. Now notice that the margin of error decreased from 0.0125 to 0.0075 when the level of confidence decreased from 99 to 90. The interval is therefore wider for the larger level of confidence. Here we have the 90% versus the 99. Increasing the confidence level increases the margin of error, and hence we are left with a wider confidence level. Let's look at the role of sample size and margin of error. Suppose we obtain a simple random sample of pennies minute after 1982. Construct a 99% confidence interval with n equal 35. Assume that the larger sample size results in the same sample mean, 2.464. Comment on the effect of increasing the sample size has on the width of the interval. So our critical t-value is 2.728. When we go to the formula and we replace 17 by 35, we get a lower bound of 2.456, and when we do the upper bound, we get 2.472. So let's interpret this confidence interval. We are 99% confident that the true population mean weight of pennies minute after 1982 is between 2.456 and 2.472 grams. So the margin of error decreased from 0.0125 to 0.0082 when the sample size increased from 17 to 35. So the interval is therefore more narrow for a larger sample size. So when the sample size increases, the margin of error decreases and the confidence interval is more narrow. So summarize. Margin of error: when the confidence level increases, the margin of error increases. When the sample size increases, the margin of error decreases. Thanks for watching.